Okay, continuing with kinetics, chemical kinetics. When we figure out relative rates on the sheet or your assignment that I gave you just before this, you notice that I used a balanced equation and I used the coefficients. See, when you're trying to figure out the relative rates of a reactant or a product that's produced, they actually don't occur at the same rate if, if there was a one-to-one, if they were, they each had a one coefficient, then they would be. But rate is actually dependent on stoichiometry. In other words, balanced equations, okay? So the one before, when we did these, there was a 1 here and a 1 here, so it wasn't a problem. Those rates equaled, the negative this equaled the positive this, because when you had a balanced equation, there was a 1 here and a 1 here, if you remember back. I mean, I can go back there, but you get the idea. So when I do this balanced equation, the coefficient in front of both of these was a 1, so it didn't affect it, okay? But what if it's not? What if you have, if this would have had a 2 in front of it or whatever? So when you're figuring, relative rates, you really need to look at their coefficient, because these are based on stoichiometry. They're based on the number of moles, okay? So, oh, here it is again, sorry. I know you can't see this part, it says plus HCl. But again, these are 1 to 1 to 1, so it all worked. But what if it's not, okay? What if the equation is not 1 to 1? And again, we have to use balanced equations. So what we would do here, so let's say we're doing 2 moles of ozone, that's O3, yields 3 moles of oxygen. So we got 3 moles here and 2 moles there. When we're trying to figure out the rate, we're going to have to put a number in front here, okay? For oxygen, or for ozone, excuse me, 1/2. So whatever it is, you're going to put 1 over its, whatever its coefficient is. And over here, it'd be 1 over 3. So it's the change in concentration of ozone over time, but we got to multiply by 1/2 because of this, because of our coefficient, equals the change in time over here. And again, it's a change in oxygen over time, but now it's going to be 1/3 because we got a 3 here. So by adding this 1/2 in front and this 1/3 in front, what I'm doing is I'm using the stoichiometry of that reaction. Okay? So how do we determine what the effective concentration has? Well, what we do is we look at what they call the orders of reaction, and I'm going to show you how to figure those out. We're only going to do 0, 1, 2. They can be 3, 4, 5. They can get all crazy, but if we do the first 3, you'll get the idea, and that's enough. Okay? So when we keep every concentration constant, except for one reactant. So when we take a reaction, if we put 2 reactants together and we produce our product, okay, if we're trying to figure out their rate, or what they call their order, we have to just pick one. We can't do both, because if we do both, which one's affecting it? Is it reactant A or is it reactant B? So I'm going to show you how you figure this out. And the thing you have to remember is you can only do one at a time. Okay? You can't do both reactants in one problem. You have to do reactant A first, and then reactant B, or reactant B, then A. It doesn't matter. But what you have to do is you have to look at, you'll have several different experiments, and you'll have to look at where B stays the same and A changes. And then if I'm doing B, B is going to change and A is going to stay the same. And again, I'll show you that in a minute. Okay, so I'm going to show you examples. Here we're going to have 6 experiments. Okay, we're using ammonium plus, which is a polyatomic ion, and nitrate, which is a polyatomic nitrite, sorry, ITE. Okay, so here's our reaction. Okay, all right, in experiment 1, you can see how NO2 stays the same. All right, and NH4 changes. So if I'm trying to figure out the order, the reaction order of ammonium, I'm going to use these experiments and not this, and not one down here, because I need this reactant to be the same. Okay, if I'm comparing these guys have to change and these guys have to be the same. If both of them are changing, then it's not going to do me any good to figure out the rate, because is it this one that's causing it or is it this one? So whenever you're trying to figure out they call it their order, you have to make sure that one of them isn't changing and one of them is. Okay, Now, on the other side, the bottom ones, see how this stays the same? Ammonium stays the same concentration, and these ones vary. Okay, so what I'm doing is looking how the change in concentration of ammonia affects the rate. And I have to make sure this one doesn't change. Because if they both change, is it this that's causing it, or is it this that's causing it? So I don't want to do that. So one of them has to be the same, one of them changes, and then you look at the rate. Okay, and on the bottom part here, okay, this doesn't change and this does. So this is changing the rate. That's how it works. And you look at how much this changes and how much this changes to figure out their, what they call reaction order. I'm trying to think. Okay, so we still got it there. Yeah. Okay, so how am I going to do this? All right, if you look here to here, from step 1 to step 2, this stays the same. So this is a good, if I'm going from experiment 1 to experiment 2, see how it goes from 0.01 to 0.02. I double it. Well, what happens to my rate? It goes from 5.4 times 10 to the 7 to 10.8 times 10 to the 7. It doubles. So if they both do the same thing, the reaction order is 1. Okay? Because this one's doubling and this one's doubling. Okay? I can do it with this one too. This one doubled. It went from 0.02 to 0.04. It doubled. And this one, again, these aren't in proper scientific notation, but I left them that way because it's easier to figure out. But again, this one doubled. It went from 10.8. I mean, this could have been 21.6, but 21.5 is pretty much doubling it as well. So this one doubled, this one doubled. Again, its reaction order, since they both do the same thing, is 1. Okay, let's go down here. Now again, these guys stay the same, so we use these ones. Now look what happened here. 0.0, the concentration of nitrite is 0.0202, and it doubled to 0.0404. So it's doubled. And what happened to the rate? Same thing, it doubled. So they both did the same thing. So that's a 1. Excuse me. Dogs! Okay, and then the same thing here. This doubled, this doubled. So both of these, the concentration of NH4 is 1. That's its order. And the concentration of NO2 is 1. Okay, so again, as NH4 doubles, the rate doubles. That's considered, if you want to write it all out like this, rate 2 versus rate 1, you're going to find out that it equals 1. And again, I just look at if this one doubles, and this one doubles. If this one tripled and this one tripled, since they're doing the same thing, the reaction order is 1. Okay? So if you do it like this, 2 equals 2x, x has to be 1. But again, if you just look at it, if this doubles and this doubles, it's 1. If this triples and this triples, it's 1. If this one quadruples and this one quadruples, it's 1. So if they do the same thing, their order is 1. Okay? And the same thing happens with NO2. Again, this one doubles, this one doubles. This one doubles, this one doubles. Since they're doing the same thing, again, the reaction rate is still going to be 1. Okay? So that's the first thing you have to do. You need to grab my pen. Okay. My dog just stole my pen, you guys. That's the first thing you do, is you look at what happens when one stays the same and one changes, and then that's how you can determine. So if they do the same thing, it's 1. Okay? Come here. Excuse me, I got a steel pen. Get back here. Sorry, my dog stole my pen. Okay. Once you figure out their order, you guys, then you can figure out what they call the rate law. The rate, which is this number, you can use these ones that we know to find the ones that we don't know. What you have to determine is a constant for this reaction. And when you're doing this, you can use either or. It doesn't matter. So if I was doing the rate for this one, I could plug in 5.4. I would put in 0.01 here, and then I have to put in to the watt power. Well, the watt power is the reaction. Well, in this case, it's 1. So I don't have to worry about it because, you know, any number times to the 1th power is the same number. And then I'd stick in 0.2 for this one. And again, this was a 1. So if I'm trying to figure out K, really all I have to do is take the rate and divide by the concentration of these two. Okay? So the exponents tell you the reaction order. And that's why you have to figure those out first. For both of those, the reaction order was 1. Well, if you take anything to the 1 power, the exponent of 1, it's still the same number. So those are kind of nice when they're 1. It makes it a lot easier, okay? So if I'm doing my rate, and again, you can pick, I'll go back here. You can do it for experiment 1, 2, 3, 4, 5. You're going to get the same answer, so it doesn't matter. Whichever one you want to pick, you can pick. But you plug in rate, whatever is here. For this, you put in the concentration. For this, you put in the concentration. And since they're both orders of 1, you don't have to worry about, if it was 2, which I'll show you in a minute, you'd have to put a 2 up here, okay? All right, so the exponents tell you their order, okay? So since they're both 1, you don't have to worry about it. So if I'm trying to find K, I stick in the rate from the problem, I put in their concentrations, and I solve, okay? And oh, this is a different one, okay? And that will give you K. What you use K for then is if you, let's say I want to say the concentration is this for NO2 and NH4 and they're not on the chart, you can figure out what their rate is because you have K, so you just multiply the 2 concentrations by K and then you can find unknowns. So basically you take known numbers to find K and then you use K to find unknowns, okay? So here is, we have A plus B equals C. Okay, we've got A is, this is its molarity, and B is its molarity. Okay, so now we got to figure out, first of all, the reaction order. Okay, so we got to take an experiment where one changes and where A changes and B doesn't. So I'm going to have to use 1 and 3. Okay, I'm sorry this is so blurry, I don't know why, but anyway. So 1 to 2, because B is the same over here. So it doubles, right? 1 to 2. Well, here it goes from 4 to 16. Well, 4, that's squared because 4 is 4 times as much, right? 4 times 4 is 16. So the reaction order of B isn't 1, it's 2. Because what's 4 squared? 16. So it went from 1 to 2. Here it doubled, but here it went from 4 to 16. So it didn't double. That would be a reaction order of 1. Instead, it's 4 times as much, so that'd be a reaction order of 2. Because if you take 2 squared, you get 4. That's where the 2 comes in. And now we got to do it for B as well. All right, here we got 1 to 1. So we can use, and this goes from 1 to 2. So this changes and this stays the same. So my reaction order for B, this doubles, but look what happens to the rate. It stays the same. When rate stays the same, even though I've doubled this, it means this doesn't affect it. So it's 0. So the 3 reaction orders, if the rate does not change, even though the concentration changed, the reaction order is 0, which is really nice because you don't have to figure them in when you're trying to find K. If the reaction, if it, like if this doubles and this doubles, then you know it's a 1. And if this doubles and this, quadruples, then you know it's 2. And again, if we were doing a reaction order of 3, if this doubled, this would be 3, this would be 4 to the 3rd power, so 4 times 4 would be 16 times another 3. This would have to be 64. And you can go more than that, but we're just going to go 0, 1, and 2. So this is a 2 because it doubles, but this quadruples. So that's 2 to the, 2 to the 3rd power. And then this one, it doubles, but this one stays the same, so that's 0. So that's the 3, 0, 1, and 2. Okay, so using the data, determine the rate law for the reaction, the rate constant, and the rate reaction. So in other words, we're going to find our K, and then we're going to find a rate for unknowns. But you know what? I'm going to run out of time before I can do that. So what I'm going to do is we're just going to quit here, and then I'll pick up here and show you how to solve these problems. But what I want you to practice is figuring out their reaction order, the rate. So whether the rate order for B, like I said, was 0, if it's 2, if it's 1. I'm going to have you do that next before we get into these because I want to make sure you understand that part before we start solving these problems. Okay, so that's where we'll pick up next time.